Yeah. Yeah. Okay. Maybe we can start and then when more people come. So, thank you for coming today. So the topic of today is a tutorial on how to perform fast mathematics with Numpy in Python. So this is a generic title, but as you can understand, the focus of this tutorial is Numpy. So Numpy is a package that is available in Python, whose purpose is to perform indeed high performance mathematics in this programming language. And this is the focus of today's tutorial, where we will have somehow between 2 and 3 hours of tutorial. And the idea is to have some breaks where we are going to have some few hands-on question and answer, etc. And then we see how long it takes. So the requirements is to have some basic knowledge of Python at least, and of Numpy if you ever use this package. So this would make things more interesting because we get some feedback from your side on what you're interested in. So maybe before starting, let's have a fast introduction of your background and what you are planning. So maybe if you can say your name and who you are and background, we can go around. So,
I started working with Python last year. I've done a few things, but
yeah, it's always good too. Okay. Okay. Your knowledge about Python, etc. It's okay. So you have a good knowledge of Python already. Okay, it's fine. It's okay. 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 Yeah. Thanks. Hopefully. Okay. Yeah. Go ahead. Yeah. I know my sister. Okay. So yeah, please interrupt me, make a lot of questions. The purpose of this tutorial is to be useful for you. So here I have a program. Some of you that participated already to this kind of events already may have seen part of this, but it's always good to refresh and build on it. So please, at any time, make questions and ask, okay? So let's start a bit with an introduction. No, before starting with an introduction, okay, you have already access to the slides that are available on this link. All of you are fine, right? Anybody? No? Okay. And then let me advertise this upcoming training event that it will take place in towards the end of May. And it's a two-day event. You can find it on the website. And it's going to be on data analytics in the era of large-scale machine learning. So this will be more machine learning oriented. Registration closed today, so if you want to register, you didn't do it already, please do so. Okay, yeah. Yeah, there is a mailing list of the NCC. They Stelios sends every sometimes some information about upcoming events. She just got a reminder. Probably she got it through the other, but she's not on the mailing list. I think I gave you her email address. Maybe she's not on the. It's okay. It's good to put on the mailing list everybody that replied to the tutorial series. Okay, very good. Okay, so why Python? Okay, this is maybe also interesting to go a bit around why you are using Python, but I understand many of you do it for analyzing data, basically, right? So it's something, it's either a requirement that you have for your master studies, or it's your choice, I guess, to use Python, maybe your supervisor choice, but that's it depends. But I'm very passionate about it, so let me tell you a bit why for me Python is important, and then you can, so you get some more information. So okay, Python, well, it's at the moment the most used programming language in data science. So this is one reason why all of you are getting around with it, because everybody's using it. There are other programming languages that are similar. So you have in this graph, there is R down here. R is a programming language similar to Python. Otherwise, then there are compiled programming languages like C++, C, and Fortran. So any of you having experience with C++, C, Fortran, you said it, you? Okay. So, but Python, you can see, recently is dominating the scene in programming language for this purpose. And the reasons are listed there from my side. So basically, one first important point is that it's interpreted. So you don't have to compile it. You can see immediately what you are doing and the results. It's science and data oriented. It's easy to use. There is a huge community behind. You have any issue, and you can find answers everywhere on Stack Overflow, etc. So that's also another reason that makes it great. There are a lot of libraries. It's the first choice for machine learning. And okay, we will see a bit today what makes it great. But there is all of these are positive points except the last one, which is its performance issue. So if any of you ever try to do something more serious in Python, will realize that it's slow. You don't get the performance you want. And the reason of it is because it's an interpreted programming language and not a compiled one. So we will try to see how, for instance, Numpy makes solves this issue, but there are other libraries that can do the same. Okay, so what is that makes it slow? So it makes it slow because it's, like we said, it's an interpreted programming language. So if you want to be fast, what you should use is something like C, C++, or Fortran. Those are fast codes, are fast programming languages. But the issues that are much more difficult to program, I think those of you that have some background in that, they know that. And then they need to be compiled, you keep getting errors, etc. Instead, in Python, you do something and it works. It's much easier to use. Python has two sides, and this is something we are going to explore better today. On the left is the side that everybody of you is familiar with. So this is the Python interface. There are APIs, there are packages that you can use and call. On the other side is actually how these packages are working. So the fact that there are some backends and compiled code behind them. So this is why Numpy is fast. Numpy is not just a pure Python code. It's not built on Python. It's built first on compiled languages like C, C++. It's compiled, and then it provides a Python only an API. What is an API? API stands for Application Programming Interface, and it's something. It's an interface, like the name says, that is given to the user to be able to use the package, but it does nothing on the Python side. The Python side is very lightweight. Everything is compiled behind. Okay, and so this is why it's optimal for doing fast mathematics. Indeed, again, just to remark a bit, how does an interpreted programming language work? So basically, when you are running a Python code, you write a Python code. If you're on a notebook, you press Shift Enter, and that gets executed. what is happening on the background. So you write some source code that is given to a parser. This parser will throw you some errors if you did some mistakes in writing it, and you stop there. Otherwise, it passes the code to something that converts it in a bit code. And then this byte code is interpreted and executed by using compiled libraries, and results are produced. On the other end, a compiled code is just using compiling library and producing results. So it's cutting away all this side of the chain. Okay, and this is why this is slow, because at every time you run a line of code, this needs to be parsed, converted, interpreted, and executed. While compiled library just have compiled code, and this runs very fast. And so there are many packages that employ these that provides you a way to accelerate Python. So this is something that Numpy is one of those that we are going to see today. So I divide them in two categories. There is Numpy, that is this package that allows you, like we're going to see, to do fast mathematics, data manipulation in Python. Then many of you may have got around with SciPy. SciPy is built on Numpy and provides you mathematical tools. Pandas is another very commonly used module in machine learning. And then there are these other kind of packages that whose aim is also to make Python faster, which are doing something a bit different. What they do, they compile your Python code, so you can write explicit Python code. We're going to see an example today of this. And then they compile it and execute it much faster than what it would have done before. Okay. Okay. Any questions so far? Okay. Yeah. What kernels? The kernel. Yeah, kernel. By kernel, one means a piece of code that gets compiled. So you create a kernel. It's an execution task. Okay, that's just a terminology. Okay. Yeah. Yeah, this is what we are going to see today. That's the key. Sorry, yes, I skipped that, but that's the key. The key issue that we are going to comment in a bit. About Python, that what you will do normally is to use Python, especially if you're coming from C, is to use Python like a normal programming language where you write a for loop and process the data. And that is something you should not do, okay? And we are going to see today why you should not do that, okay? And that's how to avoid it by using this other package. So that's kind of the key. Never do for loop on data using Python, okay? We are going to focus on that, okay? So, yeah, let's go and talk about Numpy. So Numpy, it became nowadays a standard for doing numeric calculation in Python. So many others, like I said, there is Pandas, you can see in PyTorch. All of these are based on the Numpy API. So if you're familiar with Numpy, then you are very familiar again with all the other kind of packages that you are available. You can then, for instance, use CuPy and run on GPUs, etc., etc. So it is a standard that is very good. It's very important to know, at least as well as you are going to know Python. So this should grow respectively. And it is the package for doing numeric calculations in Python. And you can have a look at the documentation. And this is the topic of this thing, okay? So and we can start now a bit getting our hands dirty, and we are going to move now on this online notebook, okay? The online notebook is available. You should have got the link. You can press this link, otherwise this should open this notebook here. So do you have it all open? Are you all familiar with Jupyter notebooks? Okay. So you should be able to, if you want to run it together with me, you need to open a copy of it. So you can press this under File, Open in Playground mode. Okay. So if you all do it, this opens a new Windows and run here. Okay, so this is a playground mode that I'm going to do it too. The idea of this playground mode is that you have your own execution and I can make changes without making changes to the main notebook. Okay, so this, you have copied your own execution. Okay. And now let's start talking about this topic that is, first of all, the performance. Let's comment again the performance issue of Python and on this comment that we said just before that we should not do for loops on data. So let me maybe zoom a bit in because, okay, do you all see well here? Okay, so let's talk a bit about performance. So let's try to do a very simple task, okay? And this very simple task is to do an operation. So we have two arrays, X and Y, okay? And what we want to do is to write their sum in another array, Z, okay? So how many of you will be comfortable to do this in Python? To write the sum of two arrays. So I have here below some examples, but suppose these are two arrays, two lists, okay? What will you commonly do? So if you want to do this in Python, you may want to take the length of one array, okay? So suppose I have X that is a list with some elements, and Y, it's, let's say that Y, yeah. Okay, let's say that Y is the same, and how are we going to for loop over these two set of data? If we want to sum them in Z. So let's say Z, it's a new array that we want to construct with the sum of the two. Well, one way to do it in Python, is, for instance, to do a for loop over this data, okay? So what do we need if we want to do a for loop over the data? We want to define an index I, and this I, how do we loop over data? So we can loop by doing, by changing the value of I in the length of the array, okay? So you can write range of len of X, okay? And then we said Z dot append X of I plus Y of I, okay? And then we print Z. So, it needs, at the first round, needs to connect, so just a second. 3, 2, 1, and yeah, here we got the sum of the two, okay? Do you understand this syntax? Any question here? Okay. So, but would someone have written something different? An example. Will you be able to do it in a different way? Well, you can define the length of the list. Let's say you fill it up of zeros and you write Z of I equal, okay. This is fine, okay. This is another way if you want. This is more C style. Okay, and of course it produces the same result. Okay, so this is how you will do it in Python, okay? All good. Here I've written some different ways of doing the same that, in my opinion, are increasing in performance, okay? So the first one is what I did. So these are written now in terms of a function. This is a function that takes two arguments, and it's going to sum the two arguments in an output. Okay. So the first one we do the range that we run over the value of the index. Another approach that is a bit faster is actually to get out already from X and Y their value. So the zip function, it's like the zip of your pants is going to zip the two values together. We get out the two values and we append the sum to Y. The fastest approach that you can do in Python is by doing the same that we did here, but explicitly directly in a list. So this is an inline creation of a list. You can see that instead of appending, I'm creating a list, okay? And I'm giving here the value, and I say for the two values, X and Y, in zip. So this is the values there, okay? So this is the fastest approach because we don't run a for loop, but we just create a list immediately with these values. Okay. So these are three ways. And then I have a fourth way that is X plus Y. Okay. Can this be done in Python? It's a for loop, but the difference is that while you write a for loop like this, we are doing an operation of appending. So we are really looping. The Python interpreter is going to go here, go to the next line, do the operation, append to Y, and etc. Here we are just initializing the list immediately. So what Python is going to do is going to compute the length of the list and then fill it up immediately with the values that you get. Okay, so this is quite faster. And then there is here a fourth approach that will be what one would really like to do, that is X plus Y. Can we do this X plus Y? Okay, let's try it here in a second. So can we do here X plus Y with these lists? If we try to do it, what we get this. So the last line is not meant for list. So what is the operation plus meaning for list? In this case, since these are Python lists, operation plus means concatenate them. So do a list plus the other, and we create a new list of length 8. It's not summing it, okay? It's not what our goal, okay? So you need to be careful. These are Python lists, and this is what is the operation of plus, while this last function here, it expects a NumPy array, okay? That is, if X and Y are NumPy arrays, then we can sum them. So let's see a bit this bit in a second before. Let's anticipate a second this point. So how do you use NumPy? NumPy is this package that I think many of you already used, at least once. You say import NumPy as NP. Then we can say that X array, let's name it Rx, is equal np.array of X. Ry, it's np.array of Y. And if now we print Rx, Ry, these are still the same arrays, are still the same objects, but now are arrays. And we can actually now do Rx plus Ry. Okay, so here we get the expected result because those two are NumPy array. Okay, so here we have these four functions, okay? And let's have a look now how they perform. So how do you measure usually performance of a code? If you want to check how fast it goes, how do you do it? You put a timer, okay? That's what is very normal. You take and you put a timer, and you want to time how much time it takes for run. So a way to do this in Python is the following. Here I don't want to go over this code. It's a bit a shortcut to get this timing. So basically what I'm doing here, I'm creating an array of the length. I'm creating here a list of the length of the array. So these you can see I'm using this approach that I did before, and these are these are powers of 2. So you can see what I'm doing is 2 to the power I for I in range 12, which means these array that I'm going to loop over are going to have length that are power of 2. Okay, so it's 1, 2, 4, 8 up to 2048 element. Okay, and I'm going to run for this number of elements these 4 functions 1,000 times. In this way, I'm going to measure the duration of it. Sorry, I didn't execute the functions. Okay, so in this way, we are going to measure the duration of it. So for the moment, let's not show column 4 just to, because column 4 is NumPy. And these are the times we get. So for an array of length 1, it's taking 1 millisecond. Okay, these are the timings in seconds. This is still about 1 millisecond, 2 milliseconds, 3 milliseconds. It grows, it grows, it grows. For 2048 elements are 0.6 seconds. Okay, with these 4 approaches. Okay, so let's now plot this execution time. And okay, let's plot this execution time. And what we see now, okay, you can see that there is some variance. So every time I run it, they're a bit different. But what you can see is that the time is increasing with the size, as you expect. Okay, more elements you have to process, more times it takes, right? Just a second, I'm not so happy about this plot, but we can go, yeah, this is better, okay. Okay, and now these are the first 3 methods. So you can see that the third method is faster than the other 2. Now let's see the fourth method, that is the one using NumPy. And you can see that the time that the fourth method it takes, it's here, okay. Is this a mistake? Can it be 0? You see, this fourth method is here and it's flat. Huh? Yeah, comparatively, it's very small. But is it 0? First of all, most probably it's not 0. Hopefully, it's not a mistake. Otherwise, we are getting zeros. But yeah, it's in this scale. It seems 0 because these values are very, very large. Okay. So one way to see it better is to plot everything in a log scale. And if you plot in a log scale, what you see is that the time that NumPy takes, it's here. It's of the order of 1 millisecond for any size, not like the others that are growing. This is 1 millisecond for every size. Yeah. Okay. And why is it that? Why is it flat? Why is it flat? No, it's not doing something parallel. It's just fast. But is it fast or is it Python that is slow? Okay. The answer is the second one. It's Python that is terribly slow. So this is already why you don't want to do for loops in Python, because already just for doing this loop over 2000 elements, okay, you're taking a time that is 3 orders of magnitude larger than what it would actually take with NumPy. 3 orders of magnitude. It's a factor of 1,000. Your code goes 1,000 faster just by using NumPy. Sorry? Does it affect the results? No, it doesn't affect the results. The results are the same. The major difference is that NumPy, it's compiled, while Python is looping over the data one by one. Okay? And you can see here that it's flat. Okay. So let's go back a second to the presentation. So you can see, okay, similarly to the plot of the time, there is also a plot about performance. The performance is the opposite. So here we are measuring the execution time. Instead, one uses the performance to measure how many the language is flops, so how many floating point operation per second can be done. And you can see that something that goes faster does much more operation per second. Okay. In this case, NumPy can do order of 1 million operation per second, while Python can do order of 10,000 operation per second. Okay. So this is another way to visualize the set. And okay, the question is, of course, which one is NumPy? Well, we already answered that. NumPy is the red line. Okay. And well, let's comment just to, so but do you expect NumPy to be always flat? Is this something normal? What do you expect it to do? Yeah, at some point, I mean, you would expect still a linear behavior, but in this way that is faster, but still it should grow with the number of data. Instead, it's flat. Why is it flat? Well, to understand this, let's do these are the plot of the performance. To understand this, let's run over a larger interval. So now we go up to 10 to the 20, 2 to the 20. And you can see that it was just a choice of using small amount of data to run on. This is here. While if we go to a larger amount of data, like here, then you see the time that starts increasing linearly. Okay, what are these two behaviors that we see here? So this is the expected behavior. It's increasing with the number of data. The flat region is instead the fact that in that interval, what is dominating is the cost of actually executing that call in Python. It's not the cost of doing calculations. The calculations are taking, if you extrapolate this line down, calculations are taking nothing, order of the microseconds. Okay, but there is a constant cost that is due to do this call. So there is a constant cost. So if you parameterize this function, it's an increase with the number of data plus a constant. Okay, and this constant is the constant cost of doing this data. So this is why it was so flat before. Okay, but on the other hand, I cannot run this Python code on this size because it will take forever. It will take some hours to do this point that now is taking 1 second because there is a factor of 1,000. So this is taking 1 second to be computed. With Python, it takes 1,000 seconds. You don't want to do that. The size of the array, it's limited with your memory. So you know that you can compute how much memory it takes. So these are 10 to the 6, okay? These are 10 to the 6 data. So this is a 1 million, okay? 1 million data. So these are now double numbers. If these are double numbers, these take 8 bytes each, okay? So these are times 8 bytes. And then if you want to compute how many kilobytes it is, you divide by 1024. So these are around 8 kilobytes. And you divide by 1024, these are only 8 megabytes, what we are processing of data. But you know that your RAM in your PC, what is the order of the RAM? Gigabytes. It's order of gigabytes. So we could go actually much farther. Okay, you can put order of billions of data in your in this array. Okay. So this is why you should use NumPy and not Python. Okay, this is to reply to your question about the for loops. This is why you need to run in NumPy. Okay, and let's go now on the core of the topic. So how does NumPy work? We saw a bit already how it works. So basically, the idea of NumPy is to provide a package that allows you to do manipulation of arrays. So what you do, you transform everything into an array, okay? That it's going to have a certain shape. So the shape of the array, so these are multi-dimensional arrays, can have many dimensions. And the shape of the arrays describe how much data there is inside. In this case, there are 4 numbers. And it has a fixed data type. So this is the key of NumPy. The key is not to allow to have a backend, etc. What is necessary to have such a backend is to fix the data type that your array is written in memory. Because the reason why Python is slow is because something like a list, okay, although it looks the same, a list is not fixed data type. A list can have anything inside here. I can put string, I can put numbers, and Python will never complain, right? So suppose this it's the list 1, 2, 3, 4. When I do it in Numpy, I do that. If here I put a string, okay, Numpy is going to complain because there is a mismatch. Okay, actually, what Numpy did, it converted safely to the same type of the first one, and so the content of the Numpy array now are not numbers anymore, but are all strings. Okay, and the reason why it does that is because it cannot manage different data type. Otherwise, you go back at the beginning. You need to know for each array what is the data type. Instead, the fact that the data type is fixed, so everything becomes an int, like here, it's something that will make it go fast. Because now you can forget about what is data is. What you can forget about being a list. You just loop over the data, like you would do in a C program. Okay, so this is the key, but it's also kind of the issue of Numpy, because if now I try to do something like this, I assign to the first value the value 0.5. What do you expect to happen? What is going to happen? Are you going to see? Let's do it for the list. For the list, I assign the first value 0.5, and what you get a list that has 0.5, 2, 3, 4, right? This is what you would expect. Is this going to happen with array? Yes or no? Who is familiar with C? What happens if this is an integer list and you do such a thing? No, it's not an error. Into an integer, if you put a float into an integer, what happens? The float is converted to an integer. But can you convert 0.5 to an integer? Well, you can by making it 0. Okay, so this is something you need to be aware of. So this array is a fixed data type, okay? And if you do this, Numpy is going to do like C. So you need to be a bit familiar with C and its problems. And the fact that Numpy is fast is because the data type is fixed, but then you can run in such issues. Okay, so it's not one-to-one compatible with Python. It's something you cannot put different data type inside, right? Okay, so you need to have in mind such limitations. But if you do it carefully, then you are fine. Okay, so what is the way to make it store 0.5? Well, the easy way is to say, okay, sorry, I don't need a new code, is to say that the data type that the list you want, even though I'm initializing from integers, is to say I want the D type to be float, suppose, okay? If you say that the type to be float, you can, like suggested here, you can also specify the precision of it, but let's put float. Then what you get is an array, it's an array that is converted in floats. This is telling you because now it's 1 point, it's not 1. Okay, this is now an array of floats and are not integers anymore. And so when I try to assign now, I can assign 0.5. Yeah. Okay. So you can always specify the data type. You can choose it. You can change it like I have it written here. So you have an array, you can change the data type in a different one, like I'm doing here. Or in the same way, you can change the shape of the array. So if it's an array of shape 4, what you can also do is to reshape it, and suppose this is 2 by 2, and then now instead of being a list, it's an array. You can see this was a double precision array. I say as integer, everything becomes integer. I reshape. If I reshape it without changing the type, instead I get still the same. Okay. Okay. Questions? No questions? No. So this is why this is this was an introduction to Numpy, to the package. So basically what we said, let's go back here, is that we have these two key elements, the shape and the data type of the array, and then Numpy can do anything with it. Okay, it can take and do operations, etc., like we saw before, very, very fast. The important is that they have the shape and data type are fixed. Of course, you may run into issues if you try to do operations between things that have different shapes, etc., so that we are going to discuss it, like we saw before the addition. But this is the topic that is going to come after. Now let's see the simple case where we take a one-dimensional array. Yeah, and we do some operations with it. Okay. So, what Numpy offers on a first end are a set of what are named universal functions. Okay. So universal functions are operations that are divided into categories, the element-wise operation reductions. And the idea is that these are just functions that modify your data. Okay, so you have a list of data, you have two arrays, you can add them together, subtract them, multiply them, etc. You want to take the exponential of your data, you just call np.exp, and you take the exponential value of it, the log, the sign, etc. And then other kind of operations are reductions. Reductions are operations that reduce the size of your data. Okay, so basically you go from 1,000 elements to 1. These are what are named reduction operations. And the examples of these are, for instance, the sum that sums all the elements of your data, taking the average of it, standard deviation, the maximum values, the minimum value. These are named reductions. So these are also operations that you can run blindly on any data. Okay, and these are two sets of tools that you need if you want to do any kind of mathematics, any kind of data operation. Okay. So questions? Okay, let's see some examples for it. So the notebook. Okay, so an example would be, for instance, this one. So first of all, we need a way to create data. Okay, you have many ways to create data. Yeah, this is something I didn't cover now. So let's cover a second this. How do we create data? Well, it depends what you want to do. What are source of data? So source of data, for instance, you have already data in a list, okay, and you just convert them in a NumPy array. This is what we did before. You say NumPy.array of something that you already have. So we have a list of numbers. Okay. Another way to create data is to use some factory that NumPy makes available. And for instance, one possible option is to get an array full of ones. A way to do this is just to say that once, you say how many, you want 10 of them, and this creates 10 ones. You want to create an array full of zeros? Okay, you just say zeros. And this is an array full of zeros, right? Well, there are many, many other ways. You want to create an array of random number, you say rand.random, and these are 10 random numbers, random.random. Okay, so these are ways just to create data. Okay, you provide the shape, etc. And we get arrays. So for instance, now let's create an array full of ones, okay? And then let's do some operations, like you want to sum them together, you sum two like this, you sum two arrays together, you take the square root of it, and this is the result. You can do whatever you want to implement like this, okay? And these, like we said, are universal operations that are applied equally on the array. So +2, what does it mean? +2 means that we are adding 2 to all elements. Clear? Array 1 plus array 2, we are summing the two arrays together. Square root of the array, we take the square root of each single value, etc., etc. You can have some, you can play with it and do all the operations you want, okay? And if I want to say sum, for instance, the operation sum takes and sum the data, okay? So now let's skip a second this one. Let's jump to the exercise. And I want you to play a bit and try to do this exercise here, okay? So try to do this task where the idea is to plot the function x squared plus 2x plus 1, okay? And how do you do it? Well, we want to define x. So this is another way of creating an array. So this linspace, what does it mean? It means we create a linear space between the two values. So the two values here are -4 and 3, where we put 100 elements into it. Let's put 10 for now. So 10 means, you see, you go from -4 to 3, a step of 1/10 per time. And you can, this is a way to create, for instance, a linear at equal steps, okay? So this is a way to create an equal steps in X. Then we want to use this to create Y, and we want to compute the minimum value of it, and we plot it. Okay. I give you some time. So we will have few exercises like this. Like the exercises are a good way to do breaks. So we do 10 minutes break as well. There are behind some water and juice and pastries there at the end of the room. So serve yourself, and I will come to the table. So we start back. Let's give you 10 minutes now. We start back at 05. Okay. Anyway. Okay. So let's continue from the exercise. Are there any questions? General? No? Okay. So just to give you the solution here, basically what you want, or someone wants to tell me the solution, what do we want to do here? We want to compute the value of y. So what is one way to do it? Of the function? Okay. The power 2. 2 times x plus 1. Perfect. So this is how we write the function, okay? And what is Python doing here, Numpy doing here? So basically, Numpy, what is it doing? So we have, like we said before, this creates a set of values. Then y, it's going to get filled up with the result. So basically, if you suppose you get, you say y equal x, then this is equal x. So let's say we have 2x plus 1. This is, you are going to get applying this operation for every single value of x. So this is 2 times x plus 1. This starts from -4. So the first value, it's -8 plus 1, -7. And the last value is 3 times 2, 6 plus 1, 7. Okay, so you can see that this is the range that we have. And what Numpy is doing this element-wise operation for every element of x. So it's exactly what you do in mathematics, okay? This is, therefore here y, it's going to get filled up of values when we do x squared plus x plus 1. And if we want to get the minimum value of it, what do we want to do? The minimum value of the function? We can just say np.min of y, and this gives us the minimum value that the function is taking, right? Okay. And so this is what we want to put here. No, it's mean. A mean, there is a difference. Now let me, A stands for array. Anyway, mean it's this, or maybe they're the same. Not sure about it. Okay. It's a bit different, a mean and a mean. Okay, but it's the same. So this gives you the minimum value of the array. Okay. And this is the kind of plot. So what do we see here? Indeed, we see the value of the function. This is I achieved with plt.plot x and y. So I'm giving the coordinates. I'm giving coordinates and values. And then I'm drawing a line where we have the minimum, right? Now you can play more with the function. And for instance, you can say, you can add some other term. We can add sine of x. Okay. And in this way, you get a different function. So why this did not change? Well, I think it's a small change. Let me say something like that. Anyway, this should give us, yeah, now it's more significant. Okay. And you can play with it, clear. Okay. And this is the way of plotting, for instance, functions. So what is Numpy doing under the hood? So Numpy, what is doing, it's doing every single operation here and adding them together, okay? So let's go back a second to the slides. Yeah. Yeah, because matmul it's a matrix, so you don't want to X. It's not a matrix here; it's a vector. Okay. One way to do it is X times X if you want. Okay, but you need matmul that you used. It's meant only for matrices. Okay, so you need to have matrix times matrix. You can just do a multiplication. That's how you get. Okay. So let's go back a second to the slides and let's close a bit about performance. So this is a difference. So now you would achieve the same result in C, where you do a for loop, or in Python. Okay. What is the difference of the left and right hand side that I'm writing here? In terms of performance, how things are operated, etc. So they're going to produce the same result, okay? The major difference between the left and the right-hand side is that here the operations you are performed over the number, okay? Over a single number, we are doing certain operation and then store it in Y, okay? So which means you are loading the data only once as you loop over, and you store them in Y only once, okay? While when we do the operation here, like Python is doing it, like Numpy is doing it, the operations are done at every, I mean, a new array is created for every step. So basically, the first one here, when Numpy is processing this kind of array, it's doing a loop over all the X and making them squared. It creates a new array. Then I say 2 times X, a loop goes over all the X again and creates a second array. Then these two arrays, it's adding them together and creates a third array. Then we add the 1 and we get the final array y. Which one of the two is faster? The second if it's in C, but also this is compiled, but is it, yeah, which one is faster? You say the left one? You say the second one? Not in Python, suppose both are in C. The left one, you can also do it in C++, it's fine. Suppose both are compiled, but which one is faster? The left or the right? You say? The right. Antonis? So the left one, we are doing, we are creating all these intermediates array. The other, we are doing all in once. So the right. We will. So the one that is fastest here is the right one. Because it's the right one. Because like we discussed, so here it's only one for loop over the data. We are reading X only once. We do certain operation, and we write it out. When this is done instead, like in the left-hand side, we are doing 4 for loops. You see this 1, 2, 3, 4 for loops over the data. We are reading arrays 5 times because we are reading X here, we read A, another X here, etc. And we are allocating 3 extra arrays that are these A1, A2, A3. Okay, so this it's a bit more expensive than the other one. So even though Numpy is much, much faster than Python, it will never reach C performance because in C, you are going to loop over the data, right, like in the right-hand side, where you tell the compiler knows already everything you want to do. Okay, this is faster. If you compare them, this is where there is performance loss in Numpy. It's the fact that it's doing array by array, while on C you can compile all of the operation. So this is the only performance limitation of Numpy. Okay. For the rest, it achieves, for each operation, it achieves C performance. So if I'm comparing C in doing 2 times X, it would get the same performance. But if I'm start doing more and more operations, doing them in C would be faster. Okay. This is just the only performance limitation about Numpy. Okay. But it's minimal. It's not a factor of, it's minimal. But this is where you can see there's still difference. Okay. And like I say here, this issue can be solved by Numpy, but we can see it later. Okay. So this is about universal function. So the universal function, like we said here, we are doing a set of operations. You can do any kind of manipulation of your functions. Okay. You can transform them, add them, sum them, etc. And you get out the results. Okay. There is one extra point that I want to add about this that is something very, very useful, and it's about specifying the axis where a certain operation needs to be executed. Okay. So let's do this example. Suppose we have a 2-dimensional array. So let's create a 2-dimensional array. Let's say we arrange 12 elements and we reshape them with a shape 3 by 4. Linear. Yeah. So here I created a range is another way to create arrays. This creates a list of numbers that go from 0 to 12. It's the same of a range, just that is named a range because it's going to be an array. And then I'm going to reshape it 3 by 4, which means have 4 columns and 3 lines. And this is the output. Okay. So something still very nice. Like we said, I can do on the fact that it's a multi-dimensional array doesn't change something. I can do array times 2 and I get everything times 2, so it will be the same. Okay. But something additional about multidimensional array is that when you want to sum or do certain operation, you can do them axis-wise. So you can specify the axis, and for instance, I can say along axis 0. So the axes are always sorted in line, column, etc. So you need to think about which one is the fastest running. You see, this is a shape. So this array has shape 3, 4. So the axis 0 is the 3, are the number of lines, 4 are the number of columns. So if I say to sum along axis 0, what do I get? I get as output 3. I'm summing, yes, I'm summing along the axis 0. So I'm summing these 3 numbers, and I get as output 4 numbers that is the value of each column. Okay? So basically, I'm summing out the first one. This is how you should see it. And I get these are the sum of each column here. I sum along axis 1, and I'm summing over the lines. And these are the values of the lines. So this is very useful because, you know, if you are also doing things with Excel, etc., tables, often you want to do things per a certain line, certain column, and this gives you the output. Okay, this is how you should see it. So the keyword axis is very useful to do operations along a certain line. Suppose this is valid for any reduction. So I can say minimum. What does it mean, the minimum along axis 1? What do you expect as an output? The first column, yes, 0, 4, 8. And this is indeed what I get, okay? This is going to give me the minimum, okay? So, axis, yes, it's something also you should have in mind, and this, it's about universal structure, okay? Let's go to the next topic. The next topic is item accessing. So far what we saw is how to manipulate the content of the array. Okay, so basically we go from an array of a certain shape to an array that has the same shape, and we are changing its content. Another thing we might want to do then is to select parts of the array to get a certain value, change the values of certain parts of the array, etc. Let's see how this can be done inside Numpy. So this is about item accessing, modification, and slicing. Let's have a look at this kind of operations. Okay, so let's start again from here. And that's why it's so slow. Okay, so, okay, we create again an array that has a certain shape. Now are 90 elements, 10 by 9, okay? And suppose we want to access the first row. So to access the first row, what we want to get is the line 0, okay? We put a 0, and this 0 gives us the first row, okay? No surprise up to here. If we want to access the first column, suppose, how can we do that? So if you put a number here, okay, if I increase this number is going always only to access rows, right? How do I access a column instead? I want to access something on the other axis. Yeah, it was written below, but how do you do it? We want to put another number here. So if suppose I put here another number, 0, 1, here now I'm accessing the first component, which is the second actually, is the number 1 component of the first row. So 0 selects the first row, 1 selects the first column. But I want to see everything in the second column. So how do I do that? Well, one way is to use this keyword, this symbol, the column, that means taking every number in the first one. It's a slice. This is an empty slice. I take any number in the first one, in the rows, and I select the first column. So when I do this, like it's written below, I'm getting everything in the column here. But it's now it's a row. It's not a column anymore, right? You see that it's written like this, not like that. Why is it written like this and not like that? Well, because it doesn't propagate what are the dimensions, right? So the shape of these, if I say dot shape, the shape of these are how many are these? 10 numbers, and it's 10 numbers. These, if it's 10, just 10, a shape of something 10, it's a row. Okay. If I want to make it a column, then I should reshape it. How should I reshape it to make it a column? 1,10, because I want something that is one line and 10 columns. Okay. Now this will be printed correctly, but it's no, it's 10,1. Sorry. It's one column but 10 lines. Okay, because this is always sorry. This is the number of rows. This is the number of columns. So it's one column and 10 lines. And now you tell me, okay, but what is the difference between being 10,1 and being 10 only? Well, the difference is the fact that one is interpreted as a row and the other as a column. Okay, so because this guy, the one we did before, has shape 10 comma, and this is shape 10,1. So Numpy is always reading from the right to left. So this is the column index, it's not the row index. And then this becomes row index if we add a 1. Okay. Is it fine? And because you want, what is natural? If I tell you there are 10 elements, Numpy is not meant to be something for matrices, right? So it's not only row and column. You can have as many elements as you want. So if I tell you there are 10 elements, how do you figure 10 elements? 10 numbers. It's a row, right? I tell you there are 10,1 elements, then these are 10 rows and 1 column. Okay, so you just need to think it from the right to left, not from the left to right. Okay. Okay. But this is the idea. So you can, with the 2 points, you can select everything in one, and this way we get a column, okay, in the way of a row. Suppose we want to get a part of the matrix. So let's see it again. Suppose we want to get this sub-block here, okay? We want to get 4 rows and 4 columns. How do we do that? Well, we can specify ranges. So we can specify ranges. And for instance, okay, here I'm saying I take from the component 2 to 4. So these are the line 2 and 3. And here I'm taking everything up to 4. So these are 4 columns and 2 rows. And you can see that this is the content of this is the content of this pack here. So I started from row 2. This is 0, 1, 2, yeah, up to 4. Okay. Right. So this is about taking slices. Okay. Any question about this? This notation here? Yeah. It's the same in Python. So this is to take ranges. Yeah. And something extra you can do, suppose up to 6, I put another element. This means a step of 2. So I go 2 to 6, a step of 2. So I'm doing 2, 4, and then 6 is excluded. So suppose I go up to 7. This is 2, 4, and 6. Okay. So you can put another component. This means the step. That's it. Okay. So there are two kinds of ways to do things. So you can specify the range, the minimum and the upper. Okay. You can leave open the minimum, and this means anything up to 4. Okay. Or you can leave open the upper, and this means from 4 on. Okay. So this is how you specify the ranges. Okay. Any question? So only a column means everything. Left number means from 4 on. This is up to 4, and this is an interval. Okay? And you can also give a step. The step you can give only if you provide the minimum maximum. That's fine. Okay. Now, 2 other things that are interesting are, okay, all the dots that are named ellipses in Python. So dots are useful when you have a multidimensional array, okay? And you don't care about how many indexes there are here. I put dots, and I say, at the end, I take 4, okay? So independent of how many axes we have, here we are saying only from the last one, I want 4 components, okay? So this is something that works for a 2-dimensional array, like it's here, okay? So here we took 4 columns. But if the array has also more dimensions, suppose we reshape this array in a shape, let's say this is dot reshape. So these are 90 elements. We can reshape it in a shape of 3 by 3 by 5 by 2, suppose. Okay. The important when you reshape something is that it preserves the size. So these are 90 elements, and these are still 90. Okay, so this operation can be done. And now, if I want the ellipsis now comes useful because independently on the size, okay, I can say R2, I put dots, and I take the last component, okay, like this. And this gives me something that is shape 335, and I'm taking only the last one, okay? So these are, is it clear? I mean, suppose you want, so this I'm taking the last one of the last, right? Suppose I want to take a component, I want to take something from the first axis and something from the last. Then what can you do? You can still use these ellipses and put here, it's something very natural. You can put here, suppose I take the second component, dot dot 0. What does it mean? I'm taking the second components of this first one. Then I want everything here, and I take the 0. Okay? And this is another way to get access. So this is the 3.5 here. Okay? So this is something useful. Okay? Last one about accessing elements is the none. Okay? The command none, what does it do? Okay, something you can also do always with these arrays when you reshape them is to add an empty axis, which is not empty, but you suppose here when I was reshaping this one, I can add an infinite amount of ones. Why can I add an infinite amount of ones here? So here when I reshape this guy, if I want, I can always add an infinite amount of ones anywhere. Why can I do this? Perfect. I'm adding dimension of size 1. So the product of these, so this number of elements is the product of the dimension. Adding 1 means just adding something that has an empty dimension, but often it's very useful because sometimes you want to make, like we saw before, something that is aligned a column, right? So adding 1, so it's useful to say these 3 components are along this axis, not along any other. Okay, we're going to see this that this also. And so if you want an easy way to add the axis is the word none. Okay, so if I pass a none to array, I'm adding a 1 at the beginning. Okay, if I pass a none dot comma none, I'm adding a 1 at the end. Okay, let's do an exercise. Can you use the word none to get from R2 the same shape? So let's do this exercise. Okay, let's do an exercise now that it's funny. So try to use none and dots. So define this. You arrive here. You define R2 that has shape you can write it 3, 3, 5, 2. Okay, so this is the shape of R2, and I want you to use only this signature to go from R2 of this shape to R2 of this shape. Can you do it? So I want you to define R2 like this. It's not in the exercise, but just something very fast. Define R2 like this. It has this shape. And I want you to use this kind of notation to add axes at once and achieve this shape here. Okay, try a second. Is it clear or? I try. How do you put it in the middle? So this was about item accessing. Now let's talk about assignment. So the same way that you access an item like this, okay? If you put an equal at the end, then you're assigning, right? So you do you select a set of values and assign it to 0. What is it doing? Well, I'm putting 0 somewhere here. Okay, so I'm taking the component from the 2 to 4 and the component from the column 4 and 5, and you can see I'm adding 0, 0. Okay, this is simple. So this way you can change the values of components. The issue, there is an issue, is that if you, when you assign something like this, okay, you're actually changing any data that is referring to the same array. So your array started with this flat. There was the beginning, we defined this array from reshaping. So suppose now you see we have this array of shape 3352, okay, which is just a reshape of the same array. All right. And by changing components now, we change the components of any other array. Just a second. We change the components of any other array that refers to that has been created from the same set of data. So you can see here that if I write R2 now, okay, we will find these zeros also inside this R2, and you can see them there here, 0, 0, 0, 0, 0, 0. Okay, why did this happen? Because what NumPy is doing, NumPy is never creating copies of arrays, but it's always, or not always, often just giving you different views of exactly the same array. Okay, because the idea is the following: like you have here. So an array that has something that like we saw now, something that is 2 by 3, okay, is the same data that you can have unrolled, or you can have them. Sorry, this is 3 by 2. You can have it 2 by 3. Okay, this data, the fact that are visualized differently in Python, does not change the content. The numbers are always the same and exactly in the same order, right? So when what NumPy is doing, it's actually giving you what is named a view of exactly always the same data. In memory, you just have 1, 2, 3, 4, 5, 6 somewhere in your memory, on your RAM. And then what Python is seeing are different views of exactly the same data. Okay, who is familiar with C should understand this, and this is how NumPy works. Because, for instance, we have an array, okay, and the array, it's we can use this array interface that is give us some information. This guy wakes up. So we have defined an array, okay, and this array, you see, it's pointing this number that we get here in the array interface is the value of the pointer. So who is familiar with C understands this. This is the pointer in memory where it's pointing the data. And here it's just saying, so these are the data, and this is a shape 10,9. Okay. If I reshape them and I shape them, for instance, 9,10, right? I've just changed the view, but the pointer in memory, it stayed exactly the same. So this number here, you can see it's the same as this number here. Okay, so it's still pointing to exactly to the same data, but with a different shape. Okay, so modifying something in this array modifies something also in this array. Is this clear? Because this is another way that makes NumPy fast. It never creates copies. It's always only modifying the array, but without changing something. Okay, so this is the issue, that if you change the value of the array 2, you are changing also array 1. Okay, this is something you need to have in mind when you do things. Okay, it's often a problem that you may run into. Okay, any questions? How many of you did have this problem in the past? I think it's common. The problem of modifying some data and you get it modified elsewhere, right? I see you nodding that. This is the reason, because it's referring to the same data, okay? Okay. So, yeah, let's do a second, another exercise, okay? So let's do this exercise about item accessing. And what I would like you is to return, okay, to write two functions, to complete two functions here. One is named get row, one is named get column. And with these two functions, basically, it should return the list of rows and the list of column of a matrix. Okay. And you need to put some code in here. Okay. And we want to return to use them. Okay. Let's give it a try. So basically, the ideal output is like this. This is the list of row, and this is the list of columns. Okay. Okay. So if we want to get a list of rows, okay, one way to do it in one line is like this. But other ways, another option is just to say list of R. So what is this doing? It's basically converting the array in a list. Okay, the list will loop over the first index and create a list out of what it's given. And this gives us, this is the best way to get a list out of the array, okay? But you can see that it's not a list of lists, it's a list of the first components, okay? If I want to get the column, okay, if I do the list of R transposed, so this is basically, it still has the same issue before, because we are getting a list of something that is transposed, right? And we get basically the list of columns, but they don't have the shape of a column. How do we achieve them to get the shape of a column? So the big issue is that you see that r.t has shape 9,10, right? So when I do a list, I get a list of lines of length 10 are these components here. So if I want to get in one go everything, what do I need to do? Basically, if I reshape it here, what happens? If I do this, right, I'm adding directly a 1 at the end, right? And when I list it, then I get a list of what is in here. Okay. So I get as an output a list of something that is shaped 10, 1, and are columns. Right? So it's the same in one line what we were doing to reshaping here. It's still the same result. It doesn't matter. It's just an exercise, but it's to understand how many ways you can do the same thing, right? Okay. Questions? No? Okay, let's go to the next one. Someone is happy. So, okay, let's go to the last important part about Numpy. That is this last very important feature of Numpy. So now, what did we achieve so far? We understood how to make operations on an array, how to access, manipulate arrays, etc. Okay. The last step is to Okay. The last important ingredient in Numpy software, this is another very, very cool feature. It's about broadcasting. So what does broadcasting mean? Broadcasting is another very important property that allows you to do operations between arrays that have different shape. So if you try out and you and you want to suppose something that has shape 4,3 and 4,3, well, that's understandable. So basically, if I'm going to sum these two arrays, what do I get as an output? I'm getting as an output the sum of element by element, right? So I'm getting as an output something that has the 0 plus 0, and I get 0, 0 plus 1, 1, 2. And then here it's 10 plus 1, here, etc. I get this output here, right? Okay. So, but what you can see here is that the data are repeated per column and per row, okay? But the output is different everywhere. Why is that? Even though here starting data that are equal for every row and here equal for every column, the output is different, okay? And this is because you can see it. One is different per row, the other per column. So when I put them together, I get something that is different everywhere, right? This is understandable. But the same result can be achieved without repeating any component. So suppose instead of giving all these 0, 1, 2 and giving only a row, okay, if this is in the format of a row, Numpy still says, okay, this element is the number of elements here are the same of this one. So I sum this result for every row. Okay, this is very similar to what we were doing before. So before it's kind of similar to this, to the fact that suppose you're not surprised when if I do something like if I do something like R2 plus 3, okay, it's not surprising for you that I get 3 everywhere because I'm doing this operation everywhere, right? So in the same way, you should not be so surprised if I do R1 plus R2, where R1 is this guy and R2 is this guy. You should not be so surprised that by doing this, I get something that is 0, 1, 2 everywhere. It's just doing the same operation, the same set of data is putting them everywhere, okay? So is it fine? If I want to add things, instead of putting this per column, so you see that this is shaped 3 by 3, this set of data. So how does it know what is, when it should add it by row or by column? So it's not just matching the shape. It's not just saying, okay, is this a size 3 and then one of those is size 3, etc., and then match them. It does it from the end to the beginning. So if this is shape 3, it's trying to match the value with the last one, okay? Which means the row is added to the row, and I obtain this result. If now I want to add 0, 1, 2 to the column instead of the row, what should I do? How can I add 0, 1, 2 to the column? Sorry? Yeah, but how do I add? I have this array 0, 1, 2 and zeros, okay? How do I add them to the column instead of the row? Yeah, what should I do? I should reshape the array 1 as a column, right? So we learned this. So this array 1, right? Exactly. This array 1 now has shape 3. So array 1 is shape 3. If I want to make it a column, it should have shape 3, 1, right? So one way to do it is none, right? I'm adding a 1. Sorry, this is 1, 3. You want to add the none at the end. you say column comma none. So this now is shape 3-1. Indeed, you can see that something written like this is a column. We saw it already before. So if I do R basically, sorry, it's written below. So if I say column comma none, it's written here, I get this R3. Second, okay? I get this R3 that it's a column, right? And so if now I add these to zeros, what do I get? Well, everything that you expect, that instead of being 0, 1, 2, now it's 0, 1, 2 on every column, right? So it's just doing something very basic. I'm putting, if it's a row, I add it to every row. If it's a column, I add it to every column. And this is true for in general. If the shape is matching along certain axis, I do it alongside every axis. Now, question: what happens if I do R1 times R2? So I remind you, R1 and R2 are sorry, R1 plus times R3, sorry. R1 and R3 are one line and one column. If I try to multiply them together, what happens? Or add them? Sorry? I get a 3 times 3 matrix, yes. And the result is, okay, it's going to be written here. So the shape, what is it? It's 3 by 3 because, like you say, I don't understand why. It's a browser. Anyway. So the shape, you can see that the shape is 3, 1. Sorry, it's 1, 3, 3, 1, and 3 by 3. The output is 3 by 3. And the result is this one, where I have for every entry the sum of the given column with the beline and column, right? And this is the output. Okay. So this is something very powerful because it allows you to change all in once an array. Okay. I will give you an example in a bit. Well, let's do something that you all learn at school. If you want to do the matrix, the table of products, what can you do? Well, you can do a range between 1 and 10, okay? And if I do these times x column comma none, I get then a matrix that has all the respective products. This is what you have on your books of the primary school, right? Is the table of multiplications. So it's you have for a given line the output of the column, right? And this you obtain it because you just do the product of these two repeated everywhere. Okay, this is a very powerful thing because it allows you to avoid repetition. So if you want to create such a table, you don't have to create the same number of columns and the same number of lines and then multiply them, but you just need to do line by column, right? So like an external column. Is it okay? So the important is to have the shape that is matched right by left. So you see this 3 goes on the right. So if the shape is smaller, it goes to the rightmost. Okay? Any questions? Okay. So let's show you an application of this. It is a nice application, suppose. If I can scroll up. possible. Okay, let me try to restart this. Sorry, just a second. Hmm? Yeah, it was like an external product of two vectors. So an application of this could be, we can see it here. So if I take what we did before, x squared plus 2 times x plus 1. Okay, let's do this the same thing I did before here. But now the task, what we want to do, we want to plot the same function with, instead of having 1 here, okay, to have an n, where n takes different values, okay? So suppose I want to plot the same function for different set of values, okay? What can I do? Well, what I can do is to make, to add here, for instance, let's create this n. So if I create an n, that is an np.arrange 10 numbers, and I add a none. This guy here now, it's a list of 10 numbers written as a column, right? This is what we learned now. So these are 0 to 10 written as a column, okay? If I do it times x here, like this, what do you expect to happen? Hmm? So what is going to happen now in the y? Well, basically what is going to happen is that when I do it, let's say with 1, y now it's a line, right? If instead of adding 1, I add n, okay, now I'm adding to every line. So if I don't put anything, this is a line with -1. So it's the same numbers, but just starting 1 below. And if I add n, now what I get is a list of lines, okay, where each of them is incremented 1 by 0, 1 by 1, 1 by 2, 1 by 3, etc., right? So here I'm getting all in once a whole list of functions, right? And so what I get, let's say this is just to make the output smaller. So what I get here, that if I try to plot them, I'm getting in the plot, I need to transpose it, sorry. I get in the plot 10 different functions where each of them is shifted of 1. Okay, because in one go, I created here 10 different y's that I'm passing to the plot, and the plot is plotting each of them differently, right? So if you want to study these are kind of cross products. So you see, I'm creating something with something that has a certain shape, then I add something a different shape, and I get a list of functions. So this is a very powerful feature, this broadcasting, because you can create, you can create combinations of dimensions and create something that, okay? So yeah. Yeah, but it's the big advantage of this is that I don't have to care about the size, because if I want to reshape this guy here properly, I should write dot reshape 4, 1, okay? But then I tell you, let's do 5 points, and then you need to go there and change 5 everywhere. And this is terrible. So the best way is to just say column comma none. And this is because they added it as a feature because it's something that people normally do to reshape stuff, because you want to put the certain dimension, certain values in the correct axis, right? So this is an easy way to achieve it. Okay. Okay, so these are the templates. Yeah, you put transpose because now what X, so the problem is that now the shape of these is 5,10, where 10 are the values, but pyplot wants it in the other way. I didn't remember neither, but anyway, pyplot, you get an error, you see the error I got here is that X and Y must have the same first dimension, and now it's 110. So pyplot is working the other way around, and I just see the easy solution is to transpose, right? So I transpose it, and this becomes 100,10. Okay. Okay. Are there questions? So this broadcasting is another feature that you need to have in mind, and that allows you to do these kind of things. It's very, very useful. So I find it useful for many applications, like this one. I want to explore a space. I mean, I want to explore a certain function. So if you want to do a 3-dimensional function, you can do it. You can do various things, manipulating a certain axis, etc. So it's very important. Broadcasting allows you. You see, there are tricks to do very complicated things in very few lines. You just need to learn how. Okay. Let's give you another task that is more difficult than where, I mean, unless you have questions, so we can either do some Q&A or do a bonus. There is half an hour left. Do you have questions, I mean, that are due to do you have questions about Numpy? I guess you are all using, so maybe, did you come here with some question that you have about your codes? No? If you want to think about it, then we can do this last bonus, and then we finished. So suppose now we want to do another task. This is a task that seems much more difficult now. Okay, the task we want to do now, this is something that it has applications in, suppose you want to take the derivative of a function. Perfect. Let's do the same before. So how do you compute the numerical derivative of a function? How do you do it? Let's do this. If I say np.linspace, let's say 0,2 times np.pi, okay? Let's say do 100 values, and this is my x, the y, it's np.sine of x, okay? And I say plot x comma y. What are we going to see? A beautiful sine function, right? So I put the range between 0 and 2 pi. So this is how you access the constant pi, right? 100 values, and this is a beautiful sine function. Okay. Now I want to take the numerical derivative of it. How do you do the numerical derivative of a function? Perfect, thank you. So the numerical derivative, you compute it by taking the difference of two consecutive points. So suppose you do y1 minus y0, okay? And then what do you need to do? Divide by the distance. Perfect. So you want to divide by x1 minus x0. So this is the derivative at 0, right? This is the derivative we compute at 0, and if we want to plot it, what do we do? we can, this is going to be, well, you know, this is the slope. This is going to be the slope. Right. Okay. So let's skip this. But if I want to compute the derivative at every point, how do I do it? Okay, so you're saying what you should do is to add an element at the beginning. Okay, this is a good point. So what you want to do is to add to y an element at the beginning. So you shift everything forward, right? And you want to take the difference. Okay, this is a solution. Okay, the problem is to add an element at the beginning of an array, but it's feasible. Okay. And then the problem is the size that is different. So let's try to do it. Let's try to do this. Y shift. How do I shift an array? How do I add something at the beginning? So to add something at the beginning, one way is to do np.concatenate. And I add a 0 at the beginning of y. So this is y2. And this is something that we should find that has a 0 at the beginning. We add an extra element at the beginning, okay? And then you say, okay, I add this extra element at the beginning, and then I do y minus y2. Is this going to work? No, because the other one is 101 elements. We remove the last element, okay? So we say column, comma, minus 1. And now are all values, okay? Perfect. So let's do the same for x. So this is the y equal this. Let's do the same for x. So I do x2, I add an element at the beginning of the x. I take the difference. Now we expect the difference of the x. What is it? It's a constant. It's the same everywhere because we have equal step. So this is the x. Okay. And now I say the f is equal the y divided by the x. Okay, this is our derivative. And what I can do now is to plot plot x comma the f, and we should find the derivative of it. It's a cosine. Okay, it worked. Okay, so this was a good solution. It's one way to do it. Is it a proper solution? It's fine because it's all it's all in Numpy. The worst would have been to do a for loop. So one way, you know, is to say def equal a list and say for I in range 100, etc., etc. You understand? I can always do something like this. I can do this and say def dot append. This is the worst. That solution is better. So I can do I plus 1, I plus 1, and I need to run up to 999 elements. Okay, this is another way to do it, right? Will give us still the same result. This is the worst, this is better, very good. The best for me is to use a roll function. So if you want to add, instead of adding something and concatenate, is to roll the data. So one way is to do np.roll, and I can roll the y of 1. And in the same way, I can roll the x of do like this. In the same way, I can do I can roll the X, but you see, NumPy offers you functions to do it, but I don't think this performs much better than the other. So your solution is very good. The important you see is to stay in NumPy all the time. Okay, there is another way to do it. Okay, so these are three different ways to do the same thing. Now I substitute the zero with the first with Rust, which is fine for this case because are periodic, but okay, it's you get a mismatch. So it's rolling. So the roll function is something that does suppose you have np.arrange 10 numbers, okay? If I roll them of -1, what you get is that the 9 goes, the 0 goes at the end, and we're rolling them of 1, okay? So what you want actually is to roll them like this. Anyhow, so we moved everything forward. Okay, these are three different ways, but the important, like we said, is to do something like this. So you understand the difference. Here we are staying in NumPy. So every single operation is done fast. So adding a 0 is just a copy of the memory with a 0 at the beginning. Here we are looping over all the data at once. Here we're looping over all the data at once. We're looping over all the data at once, and it's done. Here we are doing the loop in Python. This is no. The other two are good. Okay. Okay. Questions? No? Okay. So the last point is about NumPy. So this is something, a topic that we will explore more in another tutorial, but this is just to give an idea. So what if, okay, this is an example that is a bit more complicated, but we solved it. What if you want to do something complicated, okay? Like you want to do a convolution of a kernel, you want to do some mathematical operations that are much more complicated, and it does not exist an equivalent in NumPy, or it's very difficult for you to do in NumPy. Still, what you want to do is to never do for loops, right? So the for loops, you should never do them. But if you don't have another solution to do to achieve this result, and you want to do a for loop, okay, what is going to save you is Numba. So what is Numba? Numba is a just-in-time compiler for Python codes, and it's going to compile your Python code and make it fast like it was written for C, okay? So Numba is going to take your Python code and compile it. There is here documentation, how to install it, etc. Its usage is extremely simple, and we are going to see an example here. The point is that now what you can do is to achieve, basically the advantage is that you achieve C performance. The problem is that you need to write for loops, okay? You don't have, it's what I told you so far, you should not write for loops, but here you must write for loop because it wants to compile it. So we go back, now we want to do it like in C, okay? But I give you an example now. So if I want to do the same operation that I did here in Python, well, one way, of course, like we said, is to write a for loop like this. Okay, well, I want to do x plus 1 minus x. One way is to write a for loop like this. I write a loop over n, I do the difference, and I write the output, okay? So this you will do it, and this does not perform well, of course, okay? One way to do it is with roll, but suppose you didn't know about roll. The only way you could think about is doing it like this. Then do it, it's fine. You can write it like that. What you should use then is Numba and use the function JIT. So basically, if I take what I wrote above and I put it inside a function, okay, and I decorate it with JIT, and JIT stands for Numba JIT, okay? I decorated with JIT. So what does it mean, JIT? JIT is means just-in-time compile. So it's going to be compiled the first time I call it. So I decorate it in this way. Yeah, this is not parallel. Let's talk about parallel after. So I decorate it like this. Then Numba is going to compile it for me. Okay? So it's taking this code that is pure Python and compiles it. Another big advantage is that you can do it also in parallel. So if I want to run, you know what means running in parallel. So you want to run your CPU, you know that it has multiple cores that can do operations, and you want to distribute the work between all the cores that you have. So you want to run multi-threading. If you want to run it in parallel, a way to do it here is to run packs of the array at the same time. So suppose I divide it in two parts, and I tell one CPU to compute this part and another CPU to compute, another core to compute this part. Okay, so this it's an easy way to run in parallel things. You divide your big amount of data in sub blocks and you run them in parallel. Okay, to achieve this with NumPy wouldn't do it. NumPy does not run in parallel, but Numba still you can say parallel. And instead of writing a range, you write a p range. So this you say that this is a parallel range. And then it's dividing this range of numbers in pieces. And it's running each piece on a different CPU, on a different core. Okay? So these are two different implementations, a parallel not. And we can just run it. And we get, okay, of course, the same result, but now this guy, it's compiled. Okay? Yeah. No, on one. Unless you say, because you know, okay, this is not the topic here, but when you run in parallel, you need to be always careful about issues like race condition, because multiple processes are trying to write the same data, etc. So Numba does not try to parallelize automatically. It's like in C that you need to write a pragma OpenMP parallel for, and this is, you do it with p range. Yeah, you need to be careful. It's easy to parallelize, but you need to be careful about that. Okay. One needs to check because the issue is that you want, for using Numba, you need to explicitly write the math. You cannot use NumPy function anymore. Okay, so you need to explicitly write the content. So it's Numba is not so easy, but if you are going to write pure Python code, then Numba works well. Okay. And so this Numba compiles, and we can see then we can do again our timings. Yes, I need to reloaded it. Now it was faster. So if I run this one, then I go to the end. If we compile it, then if we run it, just a second to take the time. I'm running over a very large. Maybe I shouldn't do it like this. But it is the same. Yeah. Just a second. Okay. So if we run it, we can see that Numba, it performs as well as NumPy. So this difference done here, the first difference function is the one done with NumPy. Okay. And you can see that Numba, even if it started from Python code, it translated your Python code to a speed that it's the same as what you get with NumPy. The point is that this task you were able to do it with NumPy instead. something that you cannot do with NumPy, still you can do it with Numba very well because you write it out. Okay. Okay. Why is it? Yeah. Yeah. That is what I was going on. Yeah. So why Numba is so slow here at the beginning? These two steps are very slow compared to NumPy. So it's taking order of 1 second to do it. Because it's the first time we run the code, and as the name says, this is a just-in-time compiler. So it needs to compile this function for that specific execution. So it compiles it, and then once it's compiled, then it keeps using the same function. So it does not compile it every time. It's compiled and then keeps using it. So if I rerun this graph, you will see that then the issue is gone because we're still using the same function that was already compiled before. Okay, so you can see that now there is no jump anymore at the beginning. This jump here, okay, never mind, but okay. But okay. Ideally, if I run it again, there should be no jump. So this is just some noise. Okay. Okay. So this was it about NumPy and Numba. No, Numba, there is much more. Numba is just to make it, to introduce it, but this was it about NumPy and performance in Python. Is it compare with C? Yes, it does compare with C very well. So this problem that I was mentioning before, this is another good point. This problem that I was mentioning here, in theory, Numba should do better than NumPy doing this, because Numba is going to compile these instructions. So it's going to do only one for loop. But I don't suggest it because it's not much faster. You can see 4% fast, but you don't worry about that. Those are small numbers. It's going to take you much more time to write these. You may do mistakes than writing something like this. So don't give away productivity for performance. It's much more productive to write like this. Don't worry about that. But don't do for loops in Python. Okay. So these should produce a bit more better. So they should perform a bit better, but it's much less productive. So I'm not telling you now to start write every time a for loop. Okay. Yeah, the advantage, yes, the advantage is that still you run in parallel, something you cannot do in NumPy. A big advantage, if this is a big is something you need to run many times, then still, yes, I would suggest to compile it with Numba because you can run it in parallel. NumPy will not run in parallel. NumPy does not, but Numba would. So that's a huge speed up because if you're on an HPC system that has 48 cores, then these will run 48 times faster than that because you are running in parallel. Okay. But it's not always beneficial. Depends a bit. Okay. The best is to put on GPUs and then you forget about it. Okay. Questions. So I think we arrived at the end. Yeah. Okay. We already go over this conclusion. So other questions? Okay, thank you. So it's to give you an idea. I mean, yeah, NumPy offers you a lot of features. It's very cool. Numba also, it's compatible with NumPy arrays. There is no secret there. Yeah. Try to work to, yeah, you need, what you should get out from this is that if you are used to write for loops in Python, you should stop doing it. Find always a solution for doing things in NumPy. Okay. You can do anything in NumPy. If you don't find a way to do something in NumPy, then you can ask me, look online, etc. Or you can go to Numba, but yeah, don't do for loops. Okay. Thank you. Okay.